Hello, you're welcome. All right, so now before us is magnet and magnetism. All right, so that's what we're going to be discussing in this tutorial. Now, what's a magnet? Now, a magnet is any material that has the ability to attract or repel other magnetic materials. Okay, so magnetism is the force exerted by a magnet when they attract or repel each other. So now, of course, I'm very sure you must have actually come in contact with a magnet before, right? So one thing about a magnet is that when you bring another magnet close to a magnet, that tends to be a, a force of either attraction or repulsion depending on the polarity of the magnet, right? So that is a magnet. That's what a magnet has, the ability to attract or repel other magnetic material. Okay, that's number one. Then magnetism, all right, is actually the force exerted by magnet when they attract or repel each other. So we are gonna go forward. All right, so now let's look at the nature of magnet. Now, magnet can be found in natural state in form of magnetic ore, with two main types being magnetite, also known as iron oxide. Okay, so this is the formula, right? So naturally magnet exists as iron oxide, which of course you can call it generic. The generic name is magnetite. Okay, and of course it also exists as a lodestone. So naturally these are natural magnets. They are found in nature to have magnetic properties. Okay, magnetite and lodestone, they have naturally, okay, magnetic properties. They are not being made. Okay, they are natural. All right, so forms of magnet. Now there are two forms of magnetism. Okay, magnetism is of two forms. You have permanent magnet and the temporary magnet. Okay, now the type you're going to use depend on the application, right? There's some application where you need a permanent magnet, right? There's some application that requires just a temporary magnet, so you need to know the difference between these two magnets so that you know how where you're going to use them. All right, for now, for a permanent magnet, okay, every permanent magnet is not easily magnetized. Okay, it takes time before you magnetize, before you make them magnetic. They are not easily magnetized. Okay, but it retains its magnetism for a long time after it is being magnetized. All right, so it's not susceptible to magnetism easily, but if you eventually get uh if you eventually get magnetized, it retains its magnetism for a very long time. Example is steel. So steel is actually a permanent magnet. Okay, now, a temporary magnet is the one that can easily be magnetized and demagnetized. Example is what? Iron. That is why um in electricity, okay, alternating currents, especially, we use iron as a core for winding coil or transformers, because it happens that iron supposed to get magnetized and get demagnetized, okay, in response to the changing alternating current, so that it will actually function very well. All right, so as much as that current changes, the magnetization and the demagnetization of the ion uh supposed to be proportional, right? So that it will actually function well as an alternating current uh, component, right? So please take note of that. So now let's look at ways of making a temporary magnet. Now, the following methods are used in making a temporary magnet. Now, let's say you got a bar, you got a material that okay, you want to make it temporarily magnetic. All right, so you want to make it temporarily magnetic, and there are two ways to do that. Okay, so we have one way, and for me to actually make a, let's say, a bar, okay, that is not magnetic, to be temporary, to have magnetic properties, all I just need to do is just to bring a magnet close to it. That's what is called magnetization by induction. Okay, a process by which you makes a material that is not magnetic in nature to be magnetic by bringing it close to a magnetic material. And the process we employ, okay, One of it is known as single touch method, single touch. All right. Now, in this method, one end of the magnet is used to strike the non-magnetic bar repeatedly from one end, okay, as shown. Now, remember, a magnetic bar, every magnetic bar, right, have two poles, right? Every magnetic bar have two poles, right? Excuse me. So we have the both north and the south pole, right? So one end is north pole, while the other end is south pole. So now let's say this particular bar, okay, let's say it's a bar, it's a metal that is not magnetic, and I want to make it, or I want to make it make temporary magnet out of it, right? I can do that by a single touch. A single touch simply means that all I just need to do is to bring, okay, okay, excuse me. All I simply need to do is to bring, I will hit it with, okay, a bar magnet, but I only use one end of the bar magnet to hit it, all right? So I will start from this end, start from one, hit it from one end to another, hit it, okay? And of course, in a clockwise, once I get to this end, I'll now return back, start here, okay, hit it, okay, sequentially to one end, then return, now go back to where I started from, okay? So this is what is in a single touch. So I just use one magnet to actually do that, okay? Hit it in a in a repeated cycle. So if I do that, okay, I will end up noticing that the side that where I started from, okay, the side I started from, this particular bar now will have will become magnetic, and its polarity is gonna have an opposite polarity from the bar magnet. All right. If this is where I started the striking, all right, to this end, so this is gonna be south and this side is gonna be north. So this is actually single touch, single touch of single touch, okay, single touch method. So single touch method, so that's what you see here. Okay, so single touch method. Okay, please pardon me, this side, yeah, this side, the it's not, if I'm starting from here, all right, it's only the opposite side where I actually the side I end, okay, in the striking, that will have an opposite polarity. So this side is gonna have south and this is gonna have north, okay? As I start from here, go to this place, so this side will definitely have an opposite polarity with the striking magnet. So let me see if this magnet now is this bar is this end is south. Definitely this point is gonna be north, okay? So please take note of that. Now let's look at another method of actually achieving that. So we're gonna look at double divided touch, as you can see. So in this case, I'm using two bar magnet, okay? Of one side is, I'll be striking with two bar magnet, and this time around I'll start from the middle, not from one end, from the midpoint to okay, to both end, then I return to the midpoint. Now of course, if that being the case, this side, since I'm striking with south pole, right, this side will definitely be north pole. Now if I'm striking the other side with north pole, then that side end of the bar magnet is going to be south pole, okay? So please take note of that. So I do that repeatedly until this bar becomes magnetic. All right. So let's proceed. So let's look at the laws of magnet. Okay, now the laws of magnet is just simplified, okay, the same way we actually simplify the law of electrostatics. The law of magnetism states that like poles repels while unlike pole attracts. That simply means that, okay, if I have a north south pole, okay, there's always going to be an attraction that exists between north south pole because they are unlike pole. All right. So like pole uh repels while unlike pole attract. Now we'll talk about magnetic field. Now, magnetic field is defined as a region in the space or region surrounding a magnet or a current carrying conductor where magnetic force is being experienced. So that region in the space, okay, surrounding a magnet where magnetic force is being experienced is known as magnetic field. Now, magnetic line of force. Now, magnetic line of force is defined as the imaginary line drawn in a magnetic field which shows the direction of the North Pole. Alright, so since a magnetic field is a region where magnetic force is being experienced, for me to actually get the direction of that magnetic force, I can use an imaginary line. So an imaginary line that is drawn in that particular region in the space is what is known as magnetic line of force. Alright, so now we proceed. So now we're going to look at magnetic force due to current carrying conductor. Now we have already talked about this. We said at any time we have a conductor that is carrying current, around that conductor lies magnetic field. So a current carrying conductor has magnetic field around it. Okay. Now when we place that particular conductor carrying magnet in another magnetic field, external magnetic field, okay, it will definitely experience a force. The reason being that, okay, the conductor already have magnetic force and now it's coming to interact with external magnetic force. Okay, so there's going to be a force experience, either a force of attraction or repulsion. All right, now the question is, how do we actually evaluate that force, that magnetic force, the magnetic force of a current carrying conductor? This is the formula. The force of a current carrying conductor is given by F equal to BIL sin theta. I'm gonna, let me write that. Okay, so the force experienced by current carrying conductor is given by BIL sin theta. Alright, so let's look at what all the symbol represent. Alright, the F here is the magnetic force. The B, alright, is the magnetic field strength or magnetic flux intensity. So either you call it magnetic field strength or you call it magnetic flux intensity. Alright, and of course it's measured in Tesla. So please take note of that. It's measured in Tesla. The L, the I, of course, you know, that's electric current. Electric current flowing through the conductor. Electric current. Then the L is actually the length of the conductor, the length of the wire. Finally, the theta, okay, is the angle between the direction of the current and the direction of the magnetic field. So which simply means that when the angle, let's say theta, okay, the angle between the direction of the current, okay, and of course the field is perpendicular. When the current is perpendicular to the field, that means the force now is going to be equal to, of course, BIL, then sine, because at perpendicular direction the angle is 90 degrees, okay, sine 90. And if when you evaluate sine 90 is equal to 1, and the highest sine is actually sine 90. So the maximum sine is 490. So that means the maximum force will be experienced when the angle between the electric current and the magnetic field is perpendicular, right? So at that point now the force actually experienced by the conductor is just going to be BIL times 1, right? Sine 90 is 1. So 1 times BIL is still going to be BIL. So I hope that's well understood. Okay, so all right, so now we going to look at that in detail. So as you can see, there are two magnets here, north and south pole. In between is a conductor. All right, the conductor, this arrow shows the direction of the current. So because this conductor has, and remember horizontally, okay, between the two magnets, okay, lies the magnetic field. Okay, then the force is going to be vertical. So there are two perpendicular vectors in this particular in this diagram, okay, of that you can express whenever you put a conductor carrying current in a magnetic field. Three perpendicular vectors quantities, okay. This they are all vector quantities. One is vertical. Look at, I can use this to, excuse me, about, okay, good, okay. One is vertical, so the one that is vertical is actually the force. One is like this, okay. One goes like this along with the field. Let's say the two magnets, all right. There's one magnet here, this one, then the other magnet is found this side, okay. Excuse me. Okay, so now you discover that if this is not the wire, okay, let's say the current is horizontal, all right, then the field will actually be in the direction, the field will be pointing this way, so it's perpendicular, then the force will be pointing upward, okay. And that is why there's a particular rule, okay, that will help us to actually get that. So both the current I, the magnetic field B, and the force, these three things, they are all vector quantities and they are all perpendicular to each other, all right. They are perpendicular to each other. So as you can see, that is why if I should place this wire horizontally in this magnetic field, okay, because of the fact that the force is upward, that is why this wire will only rotate. The magnetic field will cause the wire to rotate. That is the principle behind electric motor, all right. But we'll still talk more about that, so let's actually proceed. So now let's now look at the force experienced by electric charge particle in a magnetic field, okay. Having known having known that a current actually experiences a force which is given by BIL, all right, then sine theta. So how about charge? Does a charge in the magnetic field experience force? And what's the formula for the force? Okay, remember, charge, what carries charge is electron, okay. Electrons are charge carriers. So now let's look at how we can derive that formula, right? So we already know that current is giving us the quantity of charge divided by time, and we also know that velocity, all right, is given as the displacement. This displacement is the length of the wire, all right, all over time, okay. So invariably now, if I make length to the subject here, I'm going to have length to be equal to VT. Okay, so what again do I need? So putting those into this formula, I can simply say that, okay, force is going to be equal to B, magnetic field, right, or magnetic flux density, multiplied by the current, which of course is Q all over T, right, then multiplied by the length, which is Vt, then sine theta. All right, so what I have here now, T cancels T, so that you can have now that the force by a charged particle, okay, charged particle is given as B QV, right? There is sine theta. So in terms of force on a charge, all right, we use the formula, but when we are being asked of the force on a current carrying conductor, all right, we use this one, BIL, all right. So all these two formula is used to express magnetic force due to charge or current. So please take note of that as we proceed. I think I have a question here. The question goes like this: a proton moving with a speed of 5.0 times 10 raised power minus raised power 5. So let me write down the parameters here so that we will solve that. Okay, so where are we? All right, proton moving with the speed. So the speed is 5.0. So the speed of the proton v is 5.0 times what? Times 10 raised power 5 meter per second. All right, so let's proceed. Then enters a magnetic field of flux density 0.2 Tesla. All right, the flux density of that magnetic field is 0.2 Tesla. All right, so then at an angle, the angle is 30 degrees. Calculate the magnitude of the magnetic force, given that electronic charge, proton charge, okay, both proton charge and electronic charge, they are the same, 1.6 times 10 power minus 90. So what formula are we going to apply? So this simply means that we are going to apply the formula for the force experienced by a charge, which is giving us BQV, then sine theta. So this is going to be equal to B is 0.2. Then the Q is 5 times 10 raised to the power of 5. Then sine. Okay, I've not actually. This is the V, right? I've not written the value. I've not written the value for the Q. This for V. So of course you know Q is 1.6. Excuse me. Okay, so let me give myself space so that I will insert that. So here I have 1.6 times 10 raised to the power of minus 19, right? All right, so now sine the angle is 30 degrees. All right, so let's do that. So 0.2 times 1.6 times 5. 0.2 times 1.6 times 5 then sine theta is 0.5 times 0.5, that's 0.8. Then of course for the powers of 10, you know what we do with them. So it's gonna be 10 raised power minus 19 then plus 5. So that's gonna give me 0.8 times 10. Okay, and I subtract this, 10 raised power of minus 14, if I'm not mistaken. Yes, so in standard form this is going to be 8.0 then times, all right, 10 raised power minus 15 Newton. Okay, so I hope that is well understood. All right, so let's look at more example. This one goes like this: a wire of length 10 cm carrying a current of 4.0 ampere is placed in a pole of a powerful electromagnetic of magnetic flux density. Okay, so let's just write the parameters. Okay, so now the length of the wire is 10 cm, so I'm going to write the length of the wire. Okay, so length of the wire is 10 cm, so I have to convert it to meter. Converting 10 cm to meter, that gives me 0.1 meter, right? All right, so let's go. And the current is 4 ampere Magnetic flux is 2.0. Current is 4 ampere. The magnetic flux density is 0.2, right? 0.2. All right, so having known that, so the question, calculate the force. So in this case, we know we use the formula BIL, then sine theta. So B is 0.2, then times I, the current 4, then the length 0.1 times sine theta, right? So what do we have as theta? So we're looking for the force of the one when it is parallel. Now, when it is parallel, that means the angle is 0. Parallel line, the angle between parallel line is 0. And if you should actually evaluate sine 0, sine 0 should give me 0. So everything multiplied by 0 is 0. So that force, okay, that's the I part of the question is 0. So the force is 0 the when the conductor is parallel to the magnetic field. When the magnetic field and the conductor are parallel, then the force experienced by the conductor is 0. Then our question, the maximum force, right? Remember, the maximum force occur when when the angle is 90 degrees. So the maximum force is gonna be BIL, right? Excuse me, BIL sine 90, right? Which of course sine 90 is equal to 1, so which gives me BIL. So put the value there. Already B is 0.2. The current is 4, right? 4 ampere, and the length is 0.1. So use calculator to complete that. Then what's the next? The force on the wire when it makes an angle of 60 degrees. Okay, so I. All right. So this time around, the force is going to be equal to BIL, then sine. So what's the angle this time? 60 degrees. All right, so it's still just going to be the same value you have here, but you have to multiply by sine 60. All right, so I hope that is well understood. Okay, so now here we are going to be talking about magnetic field due to solenoid coil. Now, a solenoid coil, as you can see in this diagram, is a cylindrical coil. So a solenoid is a cylindrical coil of many turns. Now, if a direct current is made to pass through it, okay, if I connect this solenoid coil through direct current, right, magnetic field will be generated around it as shown below. So passing direct current around the solenoid coil causes you find out there's magnetic field around this current conductor. We already know that. Okay, anytime there's a current conductor, there's always magnetic field around it. So this is the diagram of a solenoid coil. Now the question is how do we actually evaluate the force, right? That's okay, it's actually an advanced topic, but I will still give you the formula, right? For a solenoid coil, okay, if you want to evaluate the force, right, um is it the magnetic field, please pardon me, the magnetic field, okay, of a solenoid coil is giving us permeability, right, multiplied by the number of turns of the wire, then times number of turns per unit length of the wire, then times the area of the solenoid. Right, so this is basically it, but this is the emphasis on this is on advanced you find it in advanced physics, so I'm not going to lay more emphasis on this now. Right, okay, so we'll talk more. We're going to look at Earth's magnetic field. Okay, Earth is said to have magnetic field. We are going to study Earth's magnetic field in our next video. Right, see you in the next video. Thank you very much.